Picture the Earth. If the force holding it together suddenly shut off, our oceans would lift right off the surface and drift into space. The moon would snap off its orbit and fly away. That invisible tether keeping everything intact is gravity. Back in the 17th century, Isaac Newton described it as a natural attraction that exists between any two objects with mass. Newton realized this attraction follows specific rules. First, mass dictates strength. If you take an object and scale it up, its gravitational pull gets much stronger. But distance is the counterweight. If you move them apart, that attraction weakens rapidly. Because every single object with mass generates its own pull, the entire universe is locked together in an inescapable physical web. We often confuse mass and weight, but they measure entirely different things. Your mass is the actual amount of matter in your body, which stays constant everywhere. Your weight is the measurement of how hard gravity is pulling on that mass. Because the moon has a fraction of Earth's mass, its pull is much weaker. A person who weighs 60 kilograms on Earth would only feel a force of about 10 kilograms walking on the lunar surface. This brings up a common misconception about space travel. Despite how things look on television, true zero gravity doesn't exist in orbit. Astronauts experience microgravity because they are in a state of perpetual free fall. They are falling toward the Earth constantly, but their spacecraft is moving sideways so fast that they keep missing the ground. That sideways momentum is what keeps massive structures like the International Space Station and every other satellite suspended in a permanent fall around our planet. Orbits represent the ultimate state of balance, where gravity acts as a perpetual tether that never lets go. Newton's equations for this tether are incredibly precise. We still use his math to calculate that a rocket needs to reach an escape velocity of 11.2 kilometers per second to leave Earth behind. But there was a lingering problem. Newton could calculate exactly what gravity did, but he couldn't explain how objects were pulling on each other across millions of miles of empty space. In 1915, Albert Einstein published his theory of general relativity and finally provided the answer. Einstein proposed that mass physically warps the geometry of space and time. Planets follow the path of least resistance, rolling along the curved geometric landscape created by the sun's massive weight. When you push this geometry to its absolute limit, you get a black hole. When massive stars collapse, they puncture this fabric so deeply that even light lacks the speed to escape the boundary known as the event horizon. This intense warping creates a strange side effect, gravitational time dilation. Einstein realized that space and time are not separate stages, but a single four-dimensional fabric. When a massive object warps the space in that fabric, it also stretches the time, causing it to pass more slowly near strong gravitational fields. We see this happening today. The clocks on orbiting satellites run slightly faster than the clocks sitting on Earth, and our GPS systems require constant mathematical corrections to account for the difference. This fabric is a confirmed physical reality. In 2015, the actual ripples in spacetime, gravitational waves, were captured directly at the LIGO observatories. Gravity is the physical bending of the universe itself. On a massive scale, gravity acts as the architect of cosmic structure, clumping raw matter together to ignite stars, forge planets, and build entire galaxies. Yet, despite mastering this geometry across the cosmos, general relativity completely breaks down when we look at the microscopic scale of quantum mechanics. Physicists are still searching for a unified theory of quantum gravity that can reconcile the massive curves of space with the tiny, chaotic world of subatomic particles. The exact same invisible curvature that keeps your feet firmly planted on the ground is actively shaping the entire universe, yet the mechanism that ties the cosmic to the